Hi, in this video I'm going to talk about the camera calibration based on the Zhang's algorithm. It's a pretty famous algorithm, probably you have seen, putting a chessboard in front of the camera in different poses and then seeing those colorful points in the OpenCV and then getting the intrinsic parameter for the camera. So here I'm going to go through the algorithm, all the steps and what the theory behind it. I strongly recommend you to have a look on my other video about the camera calibration based on the DLT, because I'm not going to go through the details of projection matrix and how to do this, what is interesting and what is the extrinsic parameters. So have a look on my other video. Okay, let's get started. So we have a chessboard, and we use chessboard because it's pretty easy to find the corners like this with a Harris corner detector. Please have a look on my other video about the theory of Harris corner detector and how to implement it in MATLAB. So we got a chessboard here. We put our world coordinate system here such that x and y are in the plane of the chessboard and z is perpendicular to this plane. Because of that, all these points have the z value of 0, and x and y is pretty easy to find. This one is 0, 0, 0. This one is the size of the square. So if it's a 0, 0, 0, this is 2 a 0, 0, 0, and so on. And then here we add the y. So it's pretty easy to find the 3D pose of the points in the world coordinate system. So to get the point in the in the image plane, we just have to multiply by a projection matrix and divide by third dimension. So this is my intrinsic parameter, this is my extrinsic, rotation and translation. So because z is 0, all these this column going to be multiplied by only by 0 here. Third column multiplied by this, you can see it's always going to be 0. So we can easily omit it if it's always 0. And we get another matrix, R1, R2, and phi. And here we have x and y, and we don't have z anymore because it's always 0. We can throw it away from our equations. So what we have to do is we have to multiply this by h, by x and y and 1. We compute the u and v based on this, dividing by the third dimension and multiplying u by w prime and v by w prime, and subtract everything to get everything 0 on one side, and then put the h in a column vector. Again, have a look on my other video on the DLT. I have gone through all the steps there. So it's pretty similar here. So if I do this, I will get a matrix like this, which x and y are world coordinate position of the point in the world coordinate, and u and v are the position of the point in the camera, exactly the pixel that been turned on by the ray of light. And h is a column vector. So I apply SVD, and the last column of the SVD give me the this column vector h, which is the answer. So I write it for enough points. I make this matrix, put the rows one by one here, put in the A, compute SVD, and I will get the H. So H is equal to K, R1, R2, and T. This one. K multiplied by H is equal to this. So if I multiply this K by R1, I have the H1. H1 is the first column, H2 is the second column, and R and R2 are in column B's. So index means column. So as you can see, H1 is K R1. So if I multiply by K inverse, R1 is K inverse H1. It's the same for R2. Because of the orthonormality of the rotation matrix, this R, we have two constraints. What are those? Those comes from the orthonormality. We know that the rotation matrix is orthonormal. That means R1 and R2 and R3 are 2 by 2 perpendicular. So If I multiply them by each other, if I cross product them, I will get 0, and the size of them is 1. The size of the matrix comes from itself multiplied by transpose by itself. So R1 transpose by R1 is 1, R2 transpose R2 is 1, and if I subtract these two, 1 minus 1 should be 0. So this is 1 and 2. This is very important. Stick in your mind these two criteria that we have. We're going to use them a lot. Okay, so we know this. R1 transpose R2 is 0. We just replace R by K inverse H, and we get this. H1 transpose K inverse transpose K inverse H2 0. And you know that inverse transpose of the matrix is equal to transpose inverse. It's pretty easy to investigate. And from 2, we know that 1 minus 1 is equal to 0. So we just replace R by its value and we get this. So we will call K inverse transpose K inverse B. And it's pretty easy to see B is equal to B transpose. Why? Because if I just get the transpose from both sides, these two are just going to be flipped. So B transpose is equal to B. That means these values are equal. So 2, 3 is equal to 2, 3. It should be 3, 2. 3, 1 is 1, 3, and so on. So actually I have only 6 distinct values, not 9. Okay, let's put B here in these two equations. And let's define a new matrix, HI, B, Hj, and compute it for a different value of I and j. So 1 by 3, 3 by 3, 3 by 1, should be 1 by 1, should give us a value. So if I put the I1 and j2, I1 and j2, this should be 0. And as you can see, again, I'm looking for B, so I'm trying to write enough equations so I can separate B and a column vector and multiply by V matrix and compute the SVD again. So if I write this equation 2 times, once for I and j equal to 1 and once for I and j equal to 2, that give us this equation actually. H1 transpose B H1 and H2 transpose B H2. The subtraction should be 0 because of this. So V1 1 minus V2 2 multiplied by B, this should be also 0. So let's write this matrix. And I have to give you a warning that this is a pretty big, clumsy, ugly matrix. I've done it here. You can see this row by this column, this row by this column, and this row by this column. So this row by this column gives us this, 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 again multiplied by this column. If I multiply this by this, this by this, this by this, and separate the b's and put them on a column vector like this, I will get such a matrix. For every point, we get 2 equations. One is if I put the I and j, 1, 2, it should be 0. And the other one is if I subtract them, when they are equal, this should be again 0. V1, 1, V2, B. So this is Vij. I write it 2 times for I and j, and I write it for several points. Every point gives us 2 equations, and if you have n images, then we have a matrix of 2 by 2n rows and 6 columns. 1, 2, 3, 4, 5, 6, and this is 6 by 1. Okay, so I will get enough point. I will compute the SVD. I'm in form of the V multiplied by B equals 0. And SVD, the last column of the V transpose, U sigma V transpose. The last column of V transpose is actually the B that we are looking for. If we have this B, let's see, we can easily get this B here because these values are same of these values. Okay, So I have b equal to this value from here. Let's call this, we have it from here. And if I do the Cholesky decomposition, which decompose our matrix into L star, which is a conjugate transpose of the L, which in case we have only real values, so it's only going to be transpose, so it's going to be LLT. I have LLT. I have also one matrix multiplied by its transpose. So I can safely say L is K inverse transpose. So I can easily, and L is an upper triangular and L star is a lower, or could be flipped, which is exactly the K that we're looking for. Remember, the form K was from this form. K was upper triangular matrix. So if I get the K, I can easily find the R1, R2, and T, and find the extrinsic parameters. So that was it. That was the Zhang's algorithm. Of course, this doesn't take into account the lens distortion. If you need lens distortion, you have to do some more equations, which I can put in another video. But Zhang's algorithm was this, and hope you find it useful. I will put the code for the implementation also using OpenCV in the link in the description. Thank you.